All right, welcome to this high-yield explainer. Today, we're taking those dense, sometimes overwhelming immunology principles and, well, turning them into a totally streamlined study guide, one that is perfectly tailored for medical students prepping for board exams. If you've ever felt completely buried by the sheer number of cells, pathways, and immunoglobulins involved in human defense, you are definitely in the right place. We're going to structure this complex topic so it makes perfect logical sense, using clear concepts to make sure you actually retain this crucial info for the wards. So, here's the game plan for today. We're covering innate versus acquired immunity, humoral versus cellular pathways, primary versus secondary responses, diagnosing active versus past infections, and finally, active versus passive immunization. Let's jump right in.
Starting off with Section 1, innate versus acquired immunity.
Okay, before we start splitting our defenses into all these different categories, let's just ground ourselves in a really fundamental definition. Immunity is essentially our ultimate biological resistance. It's the absolute baseline ability of the human body to resist pretty much all kinds of invading agents, whether we're talking foreign proteins, organisms, or toxins that threaten to damage our tissues and organs. Every single concept we cover today builds upward from this basic fundamental principle of survival. Now, check out this rule of two that clearly divides our immunity into two massive branches. First up, innate immunity. Think of this as your broad shield. It's your natural, inborn, completely nonspecific first line of defense. It actually has zero antigenic specificity. Basically, it doesn't care exactly what the invader is, it just knows it doesn't belong there. And you'll see this in both vertebrates and invertebrates. Then you have the lock and key of acquired immunity. This is a whole different ballgame. It develops post-exposure and is extremely powerful, precisely because it is highly targeted to specific invading agents. It literally learns, adapts, and remembers. Let's break down the exact mechanisms executing that innate first-line defense. It is just beautifully layered. We start with anatomical barriers, the physical brick wall of your skin, the tight junctions in your mucosa, and those bronchial cilia literally sweeping away invaders. If a pathogen manages to breach that wall, boom, it meets our effector cells, neutrophils, macrophages, and natural killer cells just waiting to phagocytose the threat. Fun fact here, a single hungry macrophage can gobble up to 100 bacteria before it finally dies. Crazy, right? We've also got cell-derived factors like interferons and super harsh chemical environments. Think destructive stomach acid or chemical compounds in the blood like lysozymes. Honestly, if this innate system is impaired, severe infections are going to show up real fast.
Moving on to Section 2, humoral versus cellular pathways.
So, that acquired immunity we just talked about, it actually splits into humoral and cell-mediated branches. Humoral immunity relies heavily on B lymphocytes. These guys churn out circulating globulin molecules, antibodies, that get sent right into the blood plasma to hunt down extracellular threats. It's super effective against most bacteria hanging out outside our cells. But what if the invader manages to get inside the cell? Well, that's where cell-mediated immunity steps up. This pathway relies on T lymphocytes that become specifically sensitized. These sensitized cells engage in literal hand-to-hand combat. And for your boards, you absolutely need to know this. This cellular pathway is required to fight off viral, fungal, and parasitic infections, and critically, intracellular bacteria like Mycobacterium tuberculosis and Mycobacterium lepra. Next up, Section 3, primary versus secondary responses. Bringing back our rule of two, look at the absolute stark contrast in the waves representing memory cell dynamics here. That smaller wave, that's the primary response. It happens the very first time your body sees an antigen. It is incredibly slow to start, pretty low in magnitude, and honestly short-lived. The main first responder here is IgM, but look at the massive tidal wave of the secondary response. If you get exposed to that exact same antigen again, your body's response is totally transformed. It's rapid, massive in magnitude, and long-lived. Plus, the primary weapon gets an upgrade. Instead of IgM, the body just floods the system with IgG, IgA, or IgE. This forceful, overwhelming secondary response, that is the literal function of immunologic memory in action. So let's watch how this builds chronologically. On day 0, the antigen drops in and gets recognized. But notice this crucial lag phase between days 1 and 7. It actually takes several days for enough antibody to be produced to even show up on a serum test. After that first week, IgM finally peaks. It's only weeks later that IgG production really kicks in. But fast forward to the future, upon a repeat exposure, that lag phase is practically non-existent. The production of detectable serum immunoglobulins happens so much faster. Your system remembers, and it strikes back instantly. All right, Section 4, diagnosing active versus past infections.
Now let's translate those serum levels into actual, actionable clinical meaning for the wards. Since we know IgM peaks first and drops fast, an elevated specific IgM is a huge red flag for an active or very recent disease. On the flip side, because IgG levels hang around for a long time after the infection clears, an isolated elevation of only IgG, that just signifies a past infection. It's a past battle, not a current war. But here's your high-yield diagnostic key. If you see a rising level of specific IgM followed by a fourfold rise in IgG, that is definitively diagnostic of an active infection. A rise of less than fourfold? Meh, that might just be a generic, nonspecific immune bump. You absolutely have to look for that massive fourfold leap.
And finally, Section 5, Active versus Passive Immunization.
Notice the strict contrast here between borrowing immunity and actually building it. Passive immunization is basically an emergency stopgap. We are administering antibodies directly to a patient who's already been exposed to an infection. We might pull these from human serum, like for Hep A, or even animal serum, like for tetanus. But remember, because it's borrowed, the protection is strictly short-term. Active immunization, on the other hand, is totally proactive. We administer the antigens prior to infection to train the immune system in advance. Think childhood vaccines for polio, measles, or hepatitis B. Because we're forcing the host's body to do the actual heavy lifting, the protection induced is virtually lifelong.
This really straightforward sequence maps the exact biological mechanism behind those active childhood vaccines, and it perfectly illustrates the brilliant practical use of immunologic memory. Step 1, we administer the antigen. This could be a killed organism, an attenuated live one, or an inactive toxin. Step 2, this relatively harmless mimic safely stimulates the host's primary immune response. It pushes right through that slow lag phase we discussed earlier, totally skipping the danger of real disease. And finally, step 3, the body churns out high antibody levels and, most importantly, lifelong memory cells. The host is now permanently primed for that massive, rapid secondary response if the real dangerous pathogen ever actually shows up.
As we wrap up this explainer, I really want to leave you with a provocative thought, one that perfectly bridges today's foundational concepts right into your upcoming pathology blocks. We've spent this whole time marveling at the incredible power, specificity, and memory of the acquired immune system, right? How B cells and T cells act like these perfectly targeted microscopic snipers. But ask yourself this. What happens when this flawless targeting system glitches? What happens when that forceful, overwhelming secondary response actually loses its ability to differentiate between a foreign antigen and your own healthy cells? Just keep that question in the back of your mind as you start diving into autoimmune disorders. Thanks so much for focusing in with me today, and happy studying.